My name is Mr. Rupp, and in this video I will show you what rational expressions consist of, how to identify values excluded from the domain of a rational expression, and also how to simplify rational expressions. By the end of the video, you should be able to simplify rational expressions, identify excluded values, and then use rational expressions to solve real-world problems. Let's get started. 11-2, rational expressions. So we have some definitions that we should put up first. First of all, what is a rational expression? Okay, well, as you can see on your screen, a rational expression is an algebraic fraction whose numerator and denominator are polynomials. Aha, you say. And what is a polynomial? Okay, a polynomial. A polynomial is a monomial or a sum of monomials. All variables can only have positive whole number exponents and cannot be divided by a variable. 1 over x is not a monomial. But what is a monomial then, you say? Since now we have polynomials, but they're made up of monomials. So what are monomials? A monomial is a number, a variable, or a product of one or more variables. Okay, so xy is a monomial. All right, so much for definitions. Now we have a new definition that you need to go over, understand, a new terminology here, and it's called excluded value. Okay, any value of a variable that results in a denominator of 0 must be excluded from the domain of that variable. Division by 0, smoking hole in the city, death, doom, destruction, badness, results, right? No dividing by 0. Excluded values. Okay, now that we've got our terminology and definitions out of the way, let's do some examples. So we're going to do example 1 on page 583. Okay, and it says here, this is going to be part A. State the excluded value for this rational expression. And we have 5m plus 3 over m minus 6. Okay, so we remember now that the excluded value is any value of m that makes the original equation 0. Now it's important to note that original, okay, because later on you'll get a simplified equation and it'll be very tempting to find the excluded value of just that. And if you do, you will be wrong because you will miss some other values that the original included but the simplified did not. So in this case, the original equation here is just 5m plus 3 over m minus 6. All right, so we look at the denominator, m minus 6, and we set that equal to 0. All right, so obviously m would be equal to 6 in that case. So the excluded value then is m cannot equal 6. Let's do one that's a little more interesting, part B. X squared minus 5 over x squared minus 5x plus 6. Again, the excluded values are any values in which this denominator here would be equal to 0. So we have to set it equal to 0 to determine what those values are. All right, x squared minus 5x plus 6 is equal to 0. All right, so how do we solve this? Well, you should know this by now, right? We have to factor it. So what two factors multiplied together give you positive 6 and added together give you negative 5? Yeah. How about x minus 2, x minus 3? All right, equal to 0. Then by our zero product property, we say that either x minus 2 must equal 0 or x minus 3 must equal 0. In this case, so x would be 2 and x would be 3. So excluded values x cannot equal 2 or 3. Okay, now we're going to do an example that's a little more involved, and it utilizes a form of physics known as levers. The Egyptians used levers to their advantage to be able to move large blocks of stone around, not with ease, but they were able to move it, which is a feat considering how big some of these stones were. Okay? Had they just resorted to bare physical strength, they would never have been able to move any of these blocks that built the pyramids or the Sphinx or anything like that. Alright, so example 2 here. It says the ancient Egyptians probably used levers to help them maneuver the giant blocks they used to build the pyramids. The diagram here shows how the devices may have worked using a 10-foot lever. Okay, this problem is a little more involved than you normally see. So we're going to get some things identified right off the bat here. There are 3 components to this picture over here that you need to pay attention to, okay? One of them is, this is the effort arm, okay? This long piece right here. This next piece, which is past that point, the fulcrum point and on down, this is called the resistance arm, okay? And then you have the length of the entire bar. So over here in part A, we've got an explanation here, and I want to go through and I want to just write this out right here. L sub E is called the length of the effort arm, okay? And L sub R is the length of the resistance arm. Okay, now for the purposes of this problem, which we haven't gotten into quite yet, we're going to let little lowercase b here be the total length of the bar. So the words here say, the mechanical advantage of a lever is LE over LR, where LE is the length of the effort arm and LR is the length of the resistance arm, okay? And it says calculate the mechanical advantage of the lever the Egyptian worker is using. All right, so mechanical advantage, we'll just call it M sub A. Mechanical advantage is L sub E over L sub R. L sub E is the length of the effort arm, and from the diagram you can see that it is 8 feet. All right, L sub R is the length of the resistance arm, and you can see from the diagram that it is 2 feet. All right, so the mechanical advantage then is 4. This is a unitless number, okay, because feet cancels feet, and 8 divided by 2 is 4. So the mechanical advantage here is 4. Now, what does that mean in practical terms? Well, what it means is this. Well, however much force the Egyptian pushes down, theoretically, on the end of that bar that he's holding, okay, 4 times that amount of force is going to be exerted on the shorter end of that bar against the rock. So if he pushes down with 10 newtons of force, 40 newtons of force are going to be pushed back up against that rock, assuming that your stick there can handle that kind of force. All right, moving on to part B here. Part B says that the force placed on the rock is the product of the mechanical advantage and the force applied to the end of the lever, like we were just talking about. So if the Egyptian worker can apply a force of 180 pounds, what is the greatest weight he can lift with the lever? Let's go ahead. We'll let W equal the greatest weight, or just the weight. All right. F is going to be the amount of force that's being applied, which in this case is 180 pounds. Okay. So what it's saying here then is that the greatest weight is going to be equal to the mechanical advantage times the force that's applied. Well, in this case, W then is going to be equal to our mechanical advantage we calculated as 4, and the force that's applied is 180 pounds. All right, so 4 times 180 gives us an answer of 720 pounds. That's the greatest weight of rock that he can lift with this lever. Now let's do example 3. Okay, example 3 is going to be on page 585. And this is going to be an example of expression involving monomials. All right, so an expression involving monomials. And the expression that we are looking at is this: negative 3x squared times 4x to the 5th all over 9x to the 6th. All right, and they want us to simplify this. So how do you go about simplifying something like this? Well, these are two monomials, and they're being divided by a monomial on the bottom. So let's go ahead and find the product of the numerator. All right. So negative 3x squared times 4x to the 5th. All right. So that'll become negative 3 times 4 times x squared times x to the 5th. And that's all over 9x to the 6th. So then this becomes negative 12. Negative 3 times 4 is negative 12. And x squared times x to the 5th is x to the 2 plus 5, right? Which is x to the 7th, all over 9x to the 6th. So we need to look at 9x to the 6th and 12x to the 7th and say, how can we find greatest common factors here? Well, what's the greatest common factor between 9 and 12? Just off the top of your head, that would be 3, right? So if you took a 3 out of the top, you would end up with 3 times 4x to the 7th, and the 3 down on the bottom here would be 3 times 3x to the 6th. Now, what you're left with are the variables with their exponents. So what's the greatest common factor between x to the 6th and x to the 7th? It's x to the 6th, right? So we can further factor this then by taking out an x to the 6th. Okay? So when we take an x to the 6th out of 4x to the 7th, we're left with 4x. Okay? And when we take 3x to the 6th out of the denominator, we're left with 3. Okay? So this, I'm going to switch pen colors, just this and this cancel. All right? So what you're left with then is 4x over 3. Now for this problem, 4x over 3 happens to be 4/3 x. You should be able to recognize that, which happens to turn out to be option A for this example that's in the book. All right. 4/3 x is what this original problem simplifies down to. Let's do example 4, and that's going to be on page 585. And this is going to be an example of excluded values. All right, now we already know what those are. So here's the problem. It says simplify this guy. 3x minus 15 all over x squared minus 7x plus 10. Simplify it and find the excluded values of it. All right, so the first thing we do when we simplify is we pull out common factors. Well, in this case, in order to simplify things, we have to pull out common factors on top, but we have to factor the denominator. 3x minus 15 over x squared minus 7x plus 10 is going to be equal, well, what can we pull out of 3x plus 15? How do we factor that? Well, we can pull a 3 out. That'll give us 3 times the quantity x minus 5. All over, what are the factors of x squared minus 7x plus 10? So we have x minus 5, x minus 2. All right, we cancel, right? The x minus 5s go away here. And what we're left with then on top is 3 over x minus 2. All right. So this is the answer to the part of the problem that says to simplify it. But now we have another part of the problem that says find out what the excluded values are. Now if we take this simplified equation and we find the excluded values, we're going to find that x cannot equal 2. But there's another value x cannot equal, and if we only do it from the simplified equation, we miss that value. From the original equation over here, we look at the factored form. We look at this guy right here. That's the original equation in factored form. Okay? And in this factored form, we have x minus 5 equal to 0 and x minus 2 equal to 0. So x would be equal to 5 and x would be equal to 2. So excluded values then. Oops. X cannot equal 2 or 5. Okay? And there you have it. Excluded values, rational expressions, and polynomials, monomials. Remember that a rational expression is just a fraction, an algebraic fraction with polynomials in the numerator and denominator. You need to simplify it, and almost always you'll have to factor it and factor out common factors so that you can cancel them. Okay? Excluded values, make sure that you are calculating excluded values from the original problem, not your simplified one that you end up with. Okay, thank you for watching. I appreciate your time and attention. If you'd like, go ahead and like the video, and I will see you soon. Bye.